In our first pod of speakers this morning, I'm going to offer you a scientist and a word magician and a yogi, except that they're all kids. The youngest of them is 13, the oldest is 18, and we're going to begin with Jack Andraka. Jack. So Jack was here a couple of years ago with me and with us, and at that time, this is what Jack said.
I end up with one small paper sensor that costs 3 cents and takes 5 minutes to run. It's 168 times faster, over 26,000 times less expensive, and over 400 times more sensitive than our current standards for pancreatic cancer detection. But also, it is 100% accuracy so far in trials and can detect the cancer in the earliest stage when someone has close to a 100% chance of survival. So in the next 2 to 5 years, this patent-pending sensor could potentially lift the once dismal survival rates of pancreatic cancer from 5.5% to close to 100%. And it would do similar for ovarian and lung cancer. But it wouldn't stop there. By switching out that antibody, you could potentially detect any protein in the world, meaning any disease in the world, ranging from Alzheimer's to other forms of cancer, even HIV, AIDS, and heart disease.
So I don't know if you caught all of that, but let's take pancreatic cancer. It's one of the great killers. It's the 4th most lethal cancer around, and I know something about it because my darling sister Libby had it and beat it. And the thing about pancreatic is it never reveals itself until it's too late because it's hidden in the folds of the body. There aren't the usual manifestations that allow you to get at this thing early, and Jack, at the age of 15, figured out a disarmingly simple, totally inexpensive test that could reveal this and other cancers. So Jack, since you were with us a couple of years ago, lots been going on. I know you've got clinical trials going.
Yeah, so actually preclinical trials still running through that, and so we'll probably enter clinical trials in the next 2 to 5 years and then be on the market next 5 to 10 years. It's taking forever because of red tape, but eventually we'll get there, and now I'm working on a couple of new projects.
And it's not that you haven't been busy. I know there's been a book and there have been awards and of course.
Yeah. So I published my book, Breakthrough. It talks all about my story. And then also, what else have I graduated high school 4 days ago, so.
Why don't you tell the people what you've been up to?
All right. So I suppose my story with science really began when I was about 3 years old. My parents decided to do me and my brother's very first science experiment. They took us out into the backyard and we're like, all right, let's do some science. So it was a classic Coke and Mentos experiment where you jam a bunch of sweets down the Coke machine. And we decided to be the family that lived on the edge, took a risk, and we decided to make a rocket, the first of many rockets in the Andraka rocketry program, but this one didn't require the fire marshal to come over. And so what happened, we got all set up and it just blew straight into my face. It was like a homing missile. And my kind of passion for science kind of dwindled after that. But eventually, it wasn't the best introduction, but I finally got back on the boat and I was back with science. And I really started doing serious scientific research probably around when I was 11 or 12, when I was in 6th grade. And I had this great bowl cut. I had these big glasses. I was pretty much a Calvin Klein model, as you can see. And initially I was doing research all about civil engineering and environmental science because this is what super interested me. And I went to this middle school that really had this science fair. It was really kind of the Hunger Games of science fair. It wasn't normal science fair. They dangled a laptop above all of us and were like, go compete. And so many friendships were broken over that science fair, but I totally milked it and got 3 laptops. However, I kept doing this research and I was loving it, but then one day I came home and my mom was waiting on the front porch. And it was this devastating news that a close family friend who was an uncle to me had actually passed away from pancreatic cancer. And at the beginning of the story, I really thought, well, pancreatic cancer, I mean, when he got diagnosed, I was like, cancer, it's pretty hard, it's easier to treat than it was previously. Like, you see cancer survivors all over the place, so pancreatic cancer should be no different. But what I didn't know is that pancreatic cancer was a silent killer that killed about 95.5% of people before 5 years of diagnosis. So then I was like, okay, let me make this test. So I made that test, and then once I made it, I was like, I bet I could make this a bit cheaper. So I'm always like trying to make things cheaper and faster. So then I sat around brainstorming ideas, and that's when I came up with this kind of doodah. And essentially what it is it's this microfluidic platform, and it's made of paper, of course. And I chose paper because it's super cheap, it's pretty readily available, and also really inexpensive. And also one of the great things about paper is that it sucks things up by capillary action. And so when you're looking at blood samples or water samples, what you can do here is essentially the paper will actually filter out all the debris that will previously inhibit all these biosensors. So that's what I've been working on. And what I do is I create these different colorimetric tests that you put on those test regions. So what happens is I can just inkjet print these different biosensors there, and they change colors in 10 seconds, and they cost 1/100,000th of a single penny. So they're 100 billion times less expensive than our current methods of detection, but also they're 30 times faster. And what will happen is you'll suck up the little sample, it'll go up, and then you're able to just take a picture of this within 10 seconds on a mobile app that I created, and it will instantly tell you what's in that sample. And this is really one of the most exciting things is how inexpensive it is, because you can kind of just give this out to a bunch of people, and then they can go out to their local streams or creek or like wherever and instantly see what's in their water or what disease they have and things like that. And then you can actually geotag and timestamp all these data points and create this interactive map of the pollution in your area. So what this could do is essentially, once I take all these geotag timestamp data points together, I create this interactive map of the pollution in your area, and using these different algorithms that I create, tell you exactly where certain contaminants are coming from and how they'll be impacting your environment. So that's one part of this, but the other part is this kind of public health aspect, where I can look at, for example, in the latest Ebola outbreak, I could tell you exactly where certain strains of Ebola are happening, as well as how best treat them and where to focus our efforts and see the distribution of diseases. So that's project number one that I've been working on, and so this can be used to like really crowdsource and democratize science. And I was looking, and the future of medicine is looking really bright right now. I mean, previously, we used kind of the symptom-based diagnostic measure, where essentially we'd look at your symptoms and we'd be like, all right, you have a sore throat and that type of stuff. And then there's just a giant amount of different symptoms that you can have, or different diseases you can have. Like, I looked this up on WebMD, clearly a reliable source. And it said I could have anything from throat cancer, a cocaine addiction, or be pregnant. And the symptom-based diagnostic, it's kind of a one-size-fits-all approach, and it simply isn't personalized, and it isn't working. And it's far too generalized, and it isn't very accurate. So now we're kind of entering this new era of diagnostics, where your phone is becoming your doctor with these molecular-based diagnostics. And biomarkers are so good, these molecular-based that diagnose like these super small proteins in your bloodstream and look for these molecular cues, they're so great because what they can do is they can pinpoint and tell you exactly what disease you have. And this is one of the most exciting parts of medicine, is how we're going to have kind of these three new stages of diagnostic medicine, where first off, we have molecular, where we're able to look at every single protein in your body and know exactly where it is. So we'll be able to look at your proteome. But then we're going to be combining this with new imaging technologies, such as new MRIs and new CAT scans that are able to overlay this protein data until we'll be able to create actually an interactive video of where each and every protein is in your body at every single moment and have a complete picture of your proteome. But then we're going to be combining it with the next generation of diagnostics, genetics. We're able to low-cost sequence your entire genome. I mean, the cost of the genome is coming down exponentially. And you're able to combine that with these two previous things and have an unprecedented look at your health. And so that's one of the most exciting parts in diagnostic medicine. But then I was thinking, well, once we get to this kind of stage 0 medicine, where we're predicting that you have a disease even before you get it, we're going to have to figure out how to treat these cancers and treat these different diseases. So I was thinking, looking around, and I'm like, why don't we just like put things in that beat up the cancer? And tragically, that's a bit more complicated than that. Currently, our method is we just kind of inject you up with these different drugs and hope that works on your cancer. And so I was like, well, there has to be a better way. So I devised these new things. So a lot of people have been working on these things called nanorobots, these super small robots. And so I decided to jump on the bandwagon. Currently, so there's like 5 or 10 papers out there on this subject. And so my nanorobots, essentially what they are is they're super small ones that I program using DNA. They'll actually go into your bloodstream and figure out how to treat your cancer. I program them with what's called an artificial neural network. So they'll actually learn how to treat your cancer while in your bloodstream and combine 5 different chemotherapeutic drugs with 2 other types of therapies to really personalize your treatment. They'll actually kind of evolve to treat your cancer as it develops resistances. And essentially how they work is they're these kind of like miniature suicide bombers that go in laden with either a different like molecular load, like a drug, or they can be loaded with different bits of DNA such that they can actually communicate to each other. So my nanorobots can kind of like text each other and like gang up on these cancer cells. And it's kind of like hiring the mob to take out the cancer cells in your body. You never get out. However, but what happens is then also what they can do is they can actually tinker with the genetics of your cells, because when I put these different DNA vectors in there, essentially can insert these into your cells, whatever cells I want, whether it's regular cells or cancerous cells or whatever. I can insert these genes, and for example, I can make your cells go green if I want, so a surgeon can see them during a surgery to take out your cancer. Or for example, I can make your cancer much more susceptible to certain treatments. For example, in triple-negative breast cancer, we've had a lot of success with making it more susceptible to traditional chemotherapy that was previously resistant to. And then also could actually be able to make it go through apoptosis or cell-mediated suicide. I could essentially reprogram your cells to do whatever I want using these nanorobots. And so that's super exciting because it could be used to treat genetic diseases, or like, say, for example, you have like diabetes 1, I could put in a gene that would say, okay, you should produce insulin now. And so you can do all these super cool things with these nanorobots. But one of the coolest parts of them is that they're actually made out of iron oxide, which is a super cheap material you also might know as rust. And so there's super small nanoparticles made out of rust, and they're actually great contrast agents for MRI. So I can actually see in real time these nanorobots treating your cancer and doing genetic therapy on your cells. And so those are the 2 projects I've been working on right now. The other ones relate around kind of democratizing how we look at like indoor air quality and things like that. But another thing that I'm seeing, a really disturbing trend in medicine, is this increasing closingness to the outside environment, where essentially really this is kind of generalized towards science in general, is all of the scientific articles are locked tightly behind these paywalls. And this was one of the greatest difficulties I faced on this entire journey, is that all of these scientific articles are locked tightly behind these paywalls. And that means when you want to read one, you have to cough up $35. And that exponentially raises the cost of doing research. And so, for example, especially for a young researcher, and we see all these big STEM initiatives that say we need more kids interested in STEM, but when a seminal science article costs $35 and a Katy Perry single costs 99 cents, that's a bit of a mixed message. And this isn't just a problem for high school researchers, this is a problem for everyone. You see, recently, Harvard University released a statement to its faculty and students that said, we simply can't afford to continue paying for these subscriptions. Continuing them on their current footing is financially untenable. Now, what does it say about the world of academic publishing, the flow of information, and the accessibility of knowledge, when Harvard University, the richest academic institution in the world, can't afford to continue paying for its subscriptions? By having these paywalls, we've instituted this very rigid class hierarchy where your access to knowledge is discriminated based on how much money you or your institution has. And so at the top, we have these knowledge elite, these multi-billion-dollar endowments. These universities have these huge endowments. They can afford all these articles. But even among these universities, we have a bit of stratification, where at the top, we have the knowledge billionaires, big-name universities like Harvard, Yale, MIT that can afford each and every article. And then lower down, we have state-funded institutions that don't have as large of endowments and thus can't afford all of these articles. So what we're saying is your access to information is based on how much money your school has. And this tier-based dissemination of knowledge isn't working, and it simply isn't effective. Because it's like saying to the top 10 schools, you all can teach calculus and above, whilst everyone else is relegated to only algebra. But then lower down, we have the knowledge middle class. People like you or me, we can have access to a few articles out there. We can read some open access articles, but not really everything out there. But then we have the knowledge underclass, those 5.5 billion people who lack access to the internet and are living in knowledge poverty. So what we're saying is only 0.008% of the world's population. Those are the only people who can access scientific information. So it's like taking 80 people off the streets of Toronto and saying, you guys are the only ones who can access scientific information. Everyone else, too bad for you. And then we have 85% of the world's population, 5.5 billion people who are living in knowledge poverty and can't contribute to human innovation whatsoever. But imagine if instead we could live in a knowledge democracy, where what you look like, age, or gender doesn't apply. Whether you're from China to Cambodia, from Malaysia to Mexico, whether you're a billionaire or living on less than $1 a day, you'd have the exact same access to scientific information. Because science shouldn't be a luxury and knowledge shouldn't be a commodity. It should be a basic human right. Because the minds of the people must be free, and that means the minds of everyone, not the minds of the select few who can afford these articles. Right now, talent is universal, but opportunity isn't. And we have to shift this paradigm. Because imagine, the next cure to cancer, the solution to the next water crisis, might be within the brain of someone who doesn't have access to scientific information or an adequate education. And I believe that we can shift this. Because think, if a 13-year-old who didn't quite know what pancreas was could find a new way to attack pancreatic cancer, just imagine what we all can do together. Thank you.
That's good. Oh, stay here a second. These people want to know, I want to know, what is the problem with the trials? Why do they take as long as they do?
So one of the big things about these trials is that, first off, in the US, there's this kind of Supreme Court hearing that said patients don't own their samples. So institutions actually own the samples. And in order to have a clinical trial, you have to have a giant amount of samples. And unfortunately, my lab doesn't have a huge amount of samples. Like, it has a couple hundred, but you need a couple thousand, like 10,000, to get a clinical trial. And so I have to buy those samples at sometimes $7,000 per sample. And it's a massive amount of money. But also, there's all this red tape regarding, for example, I'm still in high school and I don't know all the intricacies and legalities of a clinical trial, and so I have to go with a company. And getting a deal with a company is rather tricky. So we've been collecting data and more data in order to get those licenses done, because right now we're in talks with 6 different biotech companies about getting on the market as soon as possible. But in the US, actually, the amount of time it's taking for this is rather quick. Typically, it takes 17 years.
Oh. Is there anybody out here who can help them? No, really, the wisdom of the crowd, it must be terribly frustrating to know that there's the possibility of this tremendous contribution, and it's poking along. So we're going to stay in touch with you, and every once in a while, you're going to come back and tell us how it's going.
Sounds good.
All right, Jack. Thank you so much.
Thank you.
Yeah. Jack, this way. Yeah.